Welcome to graph analysis, and today we're talking about Katz centrality. Katz centrality reminds you a lot of the eigenvector centrality that we talked about in another video, but here things are a little bit different. Katz centrality measures the influence of knots considering both their direct and their indirect connections. So not just who a knot is connected to, but also who this knot is connected to. So what it does, it assigns scores to count direct connections and indirect connections. So it weighs them in a way of considering them as a graph. It gives more weight to nearby connections, while it reduces weight and influence to distant ones. So it matters more in Katz centrality who's really close to you than who is far away from you. And it includes a baseline score for isolated knots to ensure they have some importance at all for the network. And again, in real life, you will not do this by hand ever. This is something as well your computer program will do for you. So I walk you through this once, and then you can trust your computer that they will do it right. So again, we start with the adjacency matrix A. And here we have this really interesting formula, which looks a little bit familiar, perhaps, after looking at eigenvalue centralities. So we look for the centrality vector x. That is what we're trying to solve for in the end, where this has the Katz centrality scores stored in. We have with alpha a scaling factor, which must be less than the largest eigenvalue for the adjacency matrix A. And we have a baseline centrality vector, which we normally fill up with ones. You will see later on why this is the case. And we have the fact that the Katz centrality becomes the same as eigenvector centrality if we choose beta to be exactly a vector of 0. So we adjust the whole thing a little bit. And it's an iterative process, which means we start with an initial guess for the vector x. And if you know iterative processes, we normally start with ones, because that is something really simple and mathematically easy to calculate and to process. So we have an updating process where the new x vector follows this alpha times adjacency matrix times the old vector plus beta. And we continue to update this so long until x new, the new vector here, does not change really. So small updates are fine. Your computer program will probably stop somewhere at 64 digits or something like that when that doesn't change anymore. But here, for the sake, we will do this way more simple and just show you 2 iterations, and you will see later on how the computer solves that and what the final results are. And you have to really ensure that alpha is chosen in a smart way that you actually can converge. If alpha is chosen, for example, larger than the largest eigenvalue, your process will not converge at all. So we've seen this graph when we looked at eigenvector centrality. And you know the adjacency matrix here as well. This looks familiar. And again, you recall that the knot 2 is the most important knot here, and knot 3 is the least important one. That's what we know from eigenvector centrality. But let's go over the iterative process here and see how this process turns out and what the difference is later on in the results to eigenvector centrality. So we choose alpha to be 0.1. We have the initial vector here indicated with the 0. That this is our 0th iteration, so this is our starting point. We fill it up with ones. And we have the bias vector of ones. I'm sorry. And in the first iteration here, we have the adjacency matrix multiplied with the initial, the old x1, x0, to get a new vector. And this vector we solve with the alpha times adjacency matrix times the initial starting vector. This is where we get this 0.2, 0.3, 0.1, 0.2, 0.2. And if we add the beta to that, we have our new x1 here, which we will then use in the second iteration, which we multiply with the adjacency matrix, get this 2.4, 3.7, 1.2, solve that by multiplying it with the scaling parameter alpha, and add beta to it, and we have the new x2. And we continue doing this until this x vector barely changes anymore. And if we solve the whole thing mathematically with a computer program, we have convergence at these values here. So we run this for a couple iterations. Your computer program at one point tells you, okay, I'm done. And it gets 1.25, 1.37, 1.12, 1.26, and 1.26 as well for the last dot. So what we see here is that the node B, the second node, is the most influential one. So we have this 1.377, and node C is the least influential one with 1.12. Again, what does this tell us if we compare it to a different graph? Nothing. It's a relative thing. This is why we also scale them and normalize them. So if we look at the graph here, we have here on the bottom left the Katz centrality with the values that the program returned to us, the 1.25, and then I normalize them. So if you see the second vector here on Katz, that is normalized. They add up to 1. And here you can now compare them easier to the eigenvector that we calculated in the other video, where we actually see that, for example, the Katz centrality puts more weight for the node 1, 4, and 5. It considers them more important. But really the big difference is for node 2 and 3. So 2 is relatively less important in the Katz centrality because it also puts weight on who is the neighbors of 2 connected to, but 3 becomes suddenly way more important with the Katz centrality because it does not just matter that it's connected to 1, but it also matters that it's really easily connected to the most important node in this network, which is 2. So this is one way to see how Katz centrality puts more weights on who is your neighbors are connected to than eigenvector centrality would do.